Good morning and welcome back. Today we're going to be looking at chapter 24, which is the last chapter in unit 6. There's only 3 chapters in this unit. And this unit is on hypothesis tests and confidence intervals for sample means as opposed to the proportions. In this chapter, we're going to be looking at paired samples and blocks. This is a little bit different than the previous chapter, but what's nice is it's actually almost identical to chapter 22. So with paired data, that's paired when the observations are collected in pairs, or they can be grouped. It happens in a bunch of ways. Most common is to compare subjects with themselves before and after a treatment. So for example, if I gave you a pre-test and then we did the chapter and I gave you a post-test, that would be paired data because it's not independent. I'm taking the same people. In this case, we would not be looking at what your scores were so much. We would be looking at your change. How much did you improve during the chapter when you were actually instructed? Ideally, you'd improve a bunch, but there'd be some people that start out really good that improve. There'd be some people that start out not so good and improve. Hopefully there wouldn't be too many people who would get dumber during a chapter, but there's always that possibility. And so that's one example of where matched pairs is a super useful thing. We can look at improvement over the course of a treatment. When pairs are from experiment, it's called blocking. When they're from an observational study, it's called matching. So it means the same thing, it's just the terminology changes depending on what it is that you're doing. So if you know the data are paired, you have to take advantage of that. You cannot use the 2 sample tests like we used in the last chapter because they are not independent. That was a huge condition for those 2 sample tests. So to decide if they're paired, you have to look to see how they were collected. There's no test that'll tell you if they're paired or not. So it's in the context of the problem. And then once we know they are paired, we look at the differences, not the actual values. We take one set of values minus the other. So if I was going to do a pre-test and post-test, I would take your post-test score and subtract your pre-test score to see how much you improved. And I would do that for every single student, and then I have that set of data, how much everyone improved. And then again, it's the differences, and you ignore the original 2 sets of data. So if we're just looking at the differences, we just have one set of data. That goes back to chapter 22. We do a 1 sample t-test. A paired t-test is a 1 sample t-test. We just use the differences instead of the actual data values. The sample size is the number of pairs. So if I have 30 of you in my class, I'm going to have 30 values of how much each person improved in the course of a chapter. Your calculator or StatCrunch or whatever can find those differences super easy. You have one of them in list 1, you have one of them in list 2, and then list 3, you just make it list 1 minus list 2 or list 2 minus list 1. And it will do the subtraction for you. So you don't have to actually calculate every single difference. So we have some assumptions and conditions. These are basically the same as all of the other assumptions and conditions for all of our other tests and confidence intervals. The different one would be the paired data condition. The data must be paired. If we're using a paired test or doing a paired interval, the data has to be paired. That's how we use the differences. If they're not paired, then we couldn't. Like if we have just two different samples, we would use a two sample test. If we only have one sample, we'd use the one sample test. The independence, the differences must be independent of each other. So each individual, like you guys, if I'm doing pre-test and post-test, you guys are an independent sample. Not your pre-test score and your post-test score, but all of you. So your differences, since you are independent of each other, your differences would be independent of each other. The randomization, the randomness can happen a lot of ways. We need to focus on what the random should be. But again, generally speaking, if we're doing a problem, it'll say that it was randomly collected or collected using a simple random sample of volunteers or and whatever. The 10% condition. So when the sample is obviously small, we don't necessarily need to check the condition. But it's just the same. It can't be more than 10% of the population, because then the variation starts getting, it changes. Our formulas don't work out quite as well. Normal population assumption. We need to assume the population of the differences follows the normal model. How do you do that? You check to see if it's nearly normal or not clearly non-normal. So with your differences, make a histogram, make a normal probability plot. Remember, just a quick sketch of those to show that, hey, I checked this. It looks fairly symmetric. There's no big outliers. We'll use a normal assumption. Or we make our normal probability plot with the differences. Like, hey, it's going up. It's fairly linear. So we will assume that the population is approximately normal. Remember, never assume that it is normal. That word approximately is a magic word. It's always approximately normal. So the t-test, the paired t-test, we use a one sample test. The difference is we use the differences. So we have the mean of the differences. Now, it's very important to specify what the differences are. Which way are you subtracting? Because that will change things. If I'm doing your pre-test and your post-test score, I would want to go post-test minus pre-test to see improvement. If I went pre-test minus post-test, I'd get the same values, but they'd all be negative. And so the bigger negative number would be a good thing. So we test the hypothesis. H naught, remember the null hypothesis is generally a statement of no change. So no change means that this value will almost always be 0. We tested the mean equals 0. The mean of the differences equals 0, which means that there was no change in whatever we were doing. And then the alternative hypothesis is greater than, less than, or not equal to, the same as they always have been. The test statistic, we'll use a t-test because we won't know the population standard deviation in pretty much every case. So use a t-test. The mean difference minus 0 typically over the standard error of the differences. This is again something that you will probably never use the formula for. You'd say we're going to use a paired t-test, and then you would put it in your calculator as a t-test, fill in the values with your difference information, and hit enter, and it'll give you those values. Just like running a one sample t-test, it's the same thing. Again, you're just using the values from your differences. So from like list 3 or column 3. When the conditions are met, the null hypothesis is true. it can be modeled. E can model the sampling distribution on this statistic with student's t-model, and we can get the p-value. Oh, that's we can model the sampling distribution on the statistic with the t and get the p-value. Again, when you do the test, you're going to do it in your calculator. Don't do these tests by hand. There's no reason for that. Do it in your calculator. It'll give you your degree of freedom. It'll give you t equals. It'll give you p equals. That t and that p mean exactly the same thing as they have since we started doing these tests. P is the probability of getting the data that you got if the null hypothesis is true. The smaller the p-value, the more evidence we have to reject the null hypothesis. The t interval, same thing, same conditions. We're looking for it's the mean of the differences plus or minus the t star times the standard error of the differences. Again, you're not going to use this formula. You're going to plug it into your calculator. It's just a one sample t interval. And you plug in with the differences. You choose your confidence level, and it'll give you your interval. The interval means exactly the same thing as the intervals have meant since we started doing intervals. I am 95% confident that the mean difference between the two scores is between this and this. If the interval includes 0, that's generally not good. That means that there was not really a change. So blocking. Well, let's say instead of using match pairs, we just look at the data separately. So here we have mean differences in ages between husbands and wives. We have the wife's ages and then the husband's ages. Well, the wife's ages are going to vary normally. The husband's ages are going to vary normally. The average age of the people in the community is right around the 40. And so we have these two box and whisker plots that do absolutely no good. This does not help us compare the mean differences between husbands and wives, because chances are the people in this age are married to people here. The people in this age are married to the people in this age. The people in this age are probably there. Maybe, we don't know. Maybe it's all sorts of random. So we want to look at the difference in ages. We cannot look at them separately. Same thing if I was looking at pre-test scores and post-test scores. Pre-test, I'm going to have people that do bad. I'm going to have people that do good. Post-test, I'm going to have people that do bad and people that do good. Hopefully not as bad and hopefully better, but either way, we're looking to see how does each person improve. Here, how does each couple's age compare? So if we took the differences of the same data, we get something that looks like this. And so this looks nearly normal. It's not skewed. It's not, it is symmetric-ish. And so we'd have it. We might have an outlier out here, but it's not too close. And notice we have, this is husband's age minus the wife's age. So the positive numbers, the husband's older. The negative numbers, the wife is older. But it's important to say that because if it was flipped, then all the numbers would be flipped too. So pairing, it removes the extra variation we saw in that side and side box plot because we're just looking at the population. So the population, it spans and it's roughly normally distributed, but that does not tell us anything about the couples. So the paired design is an example of blocking. We were blocking on their maritals or their couples. So what can go wrong? Don't use a two-sample t-test for paired data. T-test or the two-sample, they have to be independent. Paired data, they cannot be independent, like the two values. Two-sample tests, the sample sizes of both samples do not have to be the same. Paired data, it does, because you have paired stuff. Like if I had a pre-test and a post-test and somebody joined or left the class in between, they just would not be counted in our stuff because we wouldn't have the two values. Don't use the pair method when the samples aren't paired. So it goes the other way. Like two sample is for when they're independent, paired is for when they're paired. You can't do one or the other, like if it's backwards. Don't forget the outliers, and that's in the differences. So it'd be in that histogram that we just saw, where it's like, well, there might be an outlier here. We did not see that at all in those side-by-side box plots. We have to look at only the differences to find the outliers, to find the shape, to find stuff like that. And then don't look for the differences in the paired groups of the side-by-side box plots or histograms, because you will not see what you are trying to find. So what have you learned? Analyzing data from matched pairs requires different inference procedures. Kind of. We're doing the one sample t-test and the one sample t interval. We're just using the difference values instead of the actual data values. So we learned to think about the design of the study. So recognize if they're matched or if they're independent. And then again, once again, like repeating myself here quite a bit because this is very important. This is not the last time I'm going to say it. Paired data cannot be analyzed using independent t procedures. That's a two sample test. You cannot do that. So learn again the importance of checking the conditions, because that's going to tell you what test you can and cannot use. The conditions are super important. We've learned that the paired t method, look at the differences, and then it's just that one sample t-test. Like it's something we already know how to do. You're not even adding a test or an interval into what we're using. We're just using the same stuff, just with slightly different data. So we have the confidence interval based on paired data, learn to test hypothesis based on paired data, and again, learn that the reasoning, it's the same. The p-value is the same thing. The confidence interval is the same thing. There's no difference there. And then lastly, tips for the AP test. Make sure to carefully define your symbols. You can subtract them in either order, but you need to say what it is. You have to label that. That is hugely important. Now, if you had, say, the husband and wife deal, you could do, we have the mean of the husband minus wife. Use that in your subscript. That might get you there, but I would specify that this is the mean of the husband minus, or the mean of husband minus wife. Like, actually write it out. Watch the direction, because for one-side tests, the order that you subtract changes. If we want to say that the we think husbands are older than the wives, then our alternative hypothesis, husband minus wife, would need to be positive, so that'd be greater than 0. But if we want wife minus husband, the same thing would be less than 0. And then read it carefully, because one of the most common AP errors is doing the two sample instead of the match pairs, or vice versa. I told you that would not be the last time I mentioned it, because here we go. One of the most common errors on this from people that, generally speaking, know what it is they're doing. They're not careful and they use the wrong test. So somebody's going to do it. Don't be that guy. Anyway, I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.